Hey guys, it's Simon and welcome back to the LibGDX tutorial series in Java, where we are going to develop a small RPG game using Tiled as a map editor and LibGDX as our framework. So in the last part, we integrated the tiled map rendering, and when we started our game, we then saw the tiled map here. We saw that the animated tiles are working, but we did not see any of the objects so far, but at least we saw something. So that one was already working. And now in this part, we are going to focus on the architecture that we are going to use in our game. And we will also create in my opinion, the core class and one of the most important classes of this project altogether, which is the tiled service class, which then takes care of loading map objects. Later on also the trigger, maybe you remember the trap from the demonstration, and other things as well. And yeah, so let's start and dive into that. So first of all, about the architecture. So one approach that I would say normal Java developers learn at the beginning when you develop some applications is that you normally have an object-oriented approach, which would mean in our case, when we develop our game, we would most likely have a class which could be, for example, a game object. The game object, maybe it's an abstract class or an interface. It has, for example, maybe a position. Maybe it has a color, maybe it has maybe a texture, a graphic. And yeah, then later on in our game, we need moving objects. So for example, the player can move. So maybe we will have a movable game object which extends the game object. And we also might have simply some static game objects like the tree, which cannot move. And there we want to split it maybe into a static game object, which also extends the game object. And yeah, further down the road, we have some special cases here and there. So we might have even more classes, more interfaces. And that would be the typical, I would say, Java approach, which I also see in a lot of I would not call that modern, but in a lot of business applications where I have worked in the past. And I personally think that these class hierarchies or the hierarchy in general normally gets out of hand rather quickly. And it's really annoying then to debug the code because you are then in the class, that class extends an abstract class, that abstract class extends another abstract class, that one has an interface, and it's really hard to understand what is really happening, where am I, where is which code segment, what is overruled in a specific class. And yeah, I would say it's a possible solution. It's not bad in general. It has its purposes, but at least for me personally, in my game development experience, so for these tiny little 2D games, I don't really like that approach. I also started out like that, and yeah, it's not, in my opinion, not that great and not that flexible in the end. An alternative approach to that is the so-called entity component system pattern, where you have more like a flat structure. So an entity, which in our case would be, for example, a game object like the player or the tree. And to put it very simple, an entity is simply an ID, like an integer or a long, and that's it. It's nothing more. It's simply an ID. And in addition to entities, you have then components. Because it's entity component system, you have, of course, component. And the component could be, for example, a transform component, which has, again, a position, maybe a scaling, maybe the rotation of our entity, something like that. Then we would have another component which is related to graphic information. There we maybe have a texture and the color and so on. And in the end, you then have a very dynamic and I would say a flat structure, because if you now want to have, maybe add also the movable example from before, we will also have a move component which has a speed, for example. And now we have with the entity component system approach, we have the flexibility to add arbitrary amount of components to our entity. So in our case, if we wanted to have the static entity from before our tree, for example, then what we just need to edit a transform component plus a graphic component. Then it has the information of a position and a scaling, and it also has a texture and a color, so it contains that information. For the player, for example, we would add a transform component, we would add a graphic component, and we would add a move component because the player can move. And yeah, as you can see here, you can simply create an arbitrary combination of these components, and depending on what kind of component you add to an entity, it then simply gets access to certain features, let's call it like that. And yeah, how does that then work? Because the components is simply just very stupid data bags. It's just a combination or a container for a couple of informations, which is necessary usually for a specific functionality in the game. For example, you need a move component, and then you have some logic where you calculate the new position, take into account the speed and things like that. And how does that work? That is then the S in entity component system. Those are then the so-called systems. So for example, we would have a move system, and the move system iterates then over entities with a transform plus move component. So a system is in itself, it's a module or a functionality which can be developed independently, so it doesn't interact or depend on other systems directly. At least that would be the ideal approach for an entity component system. So when you would have a group of developers or a team, then you can, for example, assign one team the move system part, and they would then develop a system there. And in an entity component system, you have the functionality to simply get entities with a specific component configuration. In that case, it would be transform and move component. And then you add the logic inside the move system, which would then, for example, get the speed of the move component and update the position of the transform component inside that system. Another system would be, for example, maybe a render system, let's call it like that. That one iterates over entities with a graphic component and a transform component, and then it renders the texture to the screen for all the different entities. And again, so the systems in itself, they don't really communicate directly with each other in the ideal entity component system approach. They are really independent. And that makes it very modular and nice to develop. So you have a rather flat structure, I would say, of data. You don't have a hierarchy at all. And you have your different systems for the different functionalities of the game. That is in very short terms how an entity component system works. And in LibGDX, the basic or the default entity component system is called Ashley. That is the one that we are going to use. There are a lot of other entity component system implementations out there for Java. Maybe one that you have heard is also Artemis. Another one would be Dominion. An entity component system that was developed for Kotlin, which was done by me, is called Flex, for example. So they are also in C and C++. There are dozens of entity component systems out there. So it's nothing new, I would say, that pattern or that strategy or that architecture of a game that is well known. And yeah, so we are going to use Ashley, as mentioned, because it's the default ECS in LibGDX. And in my opinion, it's also the easiest one to learn. So when compared to Artemis, which is also a common choice with LibGDX games, I personally prefer Ashley here because it's easier to use. Good, so how does that work? So what we need in Ashley for this entity component system to work, we need a so-called engine. That is the core class of the Ashley entity component system, and there are two different kinds of engines. One is simply the engine itself. Another one would be a pooled engine. What is pooling? I won't really explain that in much detail, and we don't use that in the tutorial, but it's an important piece of information that you should know. So pooling is a special kind of strategy that you can use in languages that have a garbage collector, like for example in Java, because you could imagine if for every frame, for example, if you have a particle system and you spawn and despawn hundreds or thousands of entities per frame, then the garbage collector in Java needs to work quite a lot and clean up all these objects when they are no longer needed. And when the garbage collector needs to clean up something, that is again a rather expensive operation, and that could have an impact on the frame rate of your game. And of course, players would then notice that if there is a slowdown or even a freeze in general. And so you try to avoid that. And one strategy there is a so-called pooling. I add the link in the video description below with a Wikipedia article of LibGDX where it's explained in more detail if you are interested. But the pooling, in simple terms, you never remove an object, so the garbage collector can never clean up any objects because you have a pool of objects, for example, a pool of entities, and when you need one, you get one out of the pool, an existing one. If there is no free object in the pool, then you simply create a new object instance. And when you are done with the object, you simply add it back to the pool. So you don't clean it up or remove the different references of this object. What you do instead is that you remove it back to the pool. And with that, of course, you have over the lifespan of your game, you have growing pools where you have a lot of different objects in there, which can be reused whenever you need a specific object of the type. And with that specific strategy, you then avoid garbage collection because, as explained, the pool never releases references to the objects. It's always there. So the garbage collector doesn't need to kick in and clean up anything. And that might help in certain situations where you are creating a lot of different objects. I use that always in the beginning, but the pooling itself, in my opinion, has a downside, which is that it's a little bit more annoying to implement because when you put an object back into the pool, you need to reset its state so that when you get it out of the pool again, that you have the correct values. For example, imagine you have an entity and it had a move component, for example, with a certain speed, and now you put it back to the pool and later on reuse it for a different entity, then you need to make sure that the speed information of the previous entity is correctly cleared and that the component gets initialized correctly again. So there's a little bit of an overhead when it comes to implementation with the pooling, and I don't like that a lot. And at least for my small little games, I never had a problem with the frame rate so far, so that's why I don't use pooling anymore nowadays. But it's an important functionality or strategy that you should be aware of. So if you face some slowdowns in your game, then it might be related to the garbage collector, and one strategy to solve that is pooling. And for that in Ashley, we would have the PooledEngine, which is then simply pooling the components of our entity component system. And I think also the entities most likely, that those should also get pooled. But yeah, we keep it simple. So we just use a normal engine. So we don't care about pooling here at all. And with an engine, you can then create entities, of course, but you can also add systems to it. And what we do here as a first step in this part is that we convert the logic that we had here with the map rendering. We put that now into a system and clean up the code a little bit so that we have I would say a rather simple example of how systems work. In the second part of this part here, we are then going to integrate the objects of our tiled map here, so the player, the trees, and so on. We are going to load them as an entity so that by the end of the part, we should see the player graphic and the tree graphic available and have some integration there between tiled and the entity component system in our game. But yeah, first to start simple, we will create a new system which we will add to our engine, and we called it a render system. So that system is responsible for rendering, and it needs the sprite patch. Then it also needs the viewport for the rendering information, and it might need the asset service. There I'm not 100% sure, but yeah, let's pass it in. If we don't need it, we can remove it. It will come later on then. Yeah, but for now, let's pass it like that. The systems, you can add a lot of different systems, so we can just duplicate these calls and then add, for example, later on, we will add a move system, we will add an animation system and things like that. And the order in which they get executed is simply the order in which you add them. And the order is important because you could imagine you have maybe a good example would be a damage system, and another one would be a heal system. And now if the damage system runs before the heal system, then of course an entity can die before it gets healed. So maybe it takes critical damage or lethal damage, and there would be a heal outstanding, which helps to save the entity. But if the damage system runs first and already checks maybe if an entity is dead and removes it, then an entity dies before the heal is happening. But if we swap the order around, so if the heal system runs before the damage system, then the entity would be saved, for example, because the heal is coming first and then the damage is applied. So the order is important. I think it's not a very huge importance, because in the end, what happens if we would still have that swapped around and we don't have that special case that an entity would die from a damage, it doesn't really matter in the end. So then damage is first, healing is afterwards. And in worst case, you have a delay of 1 frame, because in the next frame, when we update all the different systems, then you anyway run through all of them again, and you have then this delay of 1 frame. But still, it's something that you need to keep in mind, and sometimes the order is important. So yeah, keep that in mind. Good, then we want to override the hide method, which is for now, it's not really important, but just that you see that as well. There's a function in the engine which is called remove all entities, which simply removes then all entities from the engine so that they get cleaned up. We will use that later on when we swap between the main menu screen and the game screen. So whenever we go away from the game screen, we clean up all the entities. And when we come back to the game screen, then we load everything again. And yeah, so that is one strategy to remove everything and clean up the engine. And now in the render part, we don't do anything special anymore. We call here simply the update method of the engine and pass the delta time, and update is then simply calling or updating all the systems that we have registered before with the add system, and calls then their methods. One special thing again, which is important in my opinion, is to clamp the delta time. So the delta time is the time that has passed between 2 frames. And it could be a rather large delta time. So I don't know, maybe there's a freeze when you resize the window or something. So maybe delta time would be, I don't know, 2 seconds, a very large amount of time. And usually your game functionality will not work good with such huge delta times, because imagine if you move an entity per frame, normally it just moves a little bit. But if the delta time would be very big, for example, 2 seconds, then the entity, of course, would also move that amount for 2 seconds. And it maybe would then, for example, pass through walls because your collision check will not detect that big movement. And to avoid that, we simply clamp the delta time. So if it would be too big, then we slow it down or clamp it with 130, for example. That is just an arbitrary number. It's usually just a small number that you pick here, and I pick here 1 divided by 30 as an example. Okay, and finally in the dispose method, there we will also going to implement something so we can get all the systems which are registered in our world. And for every system, if the system is an instance of disposable, the interface, then we want to call the dispose method of that system. So that is something special. So maybe a system has some resources that you want to free up. So for example, the render system will contain the map renderer, remove that in a moment. And then from that system, we want to also call the dispose method. So get system resources also get properly cleaned up. Okay, so then what we need to do now is to create our first system. So we will create a new package. Let's call that system. And we create a new system, which we call RenderSystem. In Ashley, we have different kind of systems. There would be an interval system, which simply is a system that runs at a specific interval and doesn't interact with entities. Then there are iterating systems, which are systems that iterate over entities. And there is a special kind of iterating system, which is called a sorting iterated system, which iterates over entities, but also sorts them. And why do we need that in the render system? The reason is that our entities, when they get rendered, they need to get sorted by their y coordinate, because let me show it to you in Tiled. If this tree is behind the player like that, then the player needs to be rendered after the tree, so that it's before the tree. But if the tree is in front of the player, like here, then the player needs to be rendered first and then the tree afterwards. So that's why we need some kind of sorting before we render our entities to the screen. And that's why we are going to use a sorted iterating system. And then there are two methods that we are going to implement. processEntity, that is then the method that gets called when we call engine.update for every entity with a specific combination that we are going to create very soon, and the dispose method because we implement the disposable interface. So let's quickly move some code. So first of all, the map renderer, which gets disposed here in the game screen, we will move that call to our render system. Then also the logic that we have here, we move that for now in the processEntity method, which is not correct, but we fix that then in a moment. And we need to move the map renderer to our system here as well. And initialize it there. And I think that's it. Okay, we also need that one here. So we need a set map method or something on our render system to update the map that gets then rendered. So remove that call here as well. Then let's create here a new method, and there we pass in then the tiled map to our map renderer. And back in the game screen, we get here the system. So we will improve that in the future, but just for now that everything is working, we do it in a specific way. So we get the render system out of our engine. And then we call setMap with the map that we have loaded here before. Okay, and here the map renderer, we also need to remove that and put it inside the constructor of our render system. Okay, so coming back, we set here that we pass in the batch, the viewport, and the asset service. So let's change the signature of the constructor in the render system so that we have here available now the batch, the viewport, and the asset service. And the batch, we need to store that as well, because later on we need that then for rendering. And also the viewport, we need to store that. And asset service, I think for now, most likely we don't need it, but yeah, we have it here available. Okay, then as we see here, when we call the constructor of the sorted iterating system, it requires a family. And also it requires a comparator. So what is a family? A family is, as I've explained before, it's simply a combination of components. So for example, family all And we want to have transform.class and graphic.class. I come to that in a moment. And then we create a family for that. So basically for a family, you can have different configurations. You can say that an entity must have all components which are specified within the all call. It must have at least one component that you specify in the one method, and it must not have any component that you specify in the exclude call. So there you get a rather good flexibility when it comes to component configuration, and the family then simply contains the entities which are matching that specific configuration. So transform and graphic will be component classes that we also create in a moment. And for the comparator, so as mentioned, we want to compare by the position of our entities. So we will have comparing, and we use the transform component, and there a so-called mapper. I come to that also in a moment, and compare then simply by the transform component. Okay, then the next thing would be we want to override the update method here of our render system. When we go inside update, you see that the sorted iterating system then simply goes over all the entities of the family that we have specified, and it will call processEntity and also sort. So if we say should sort, if we set that to true, then it will sort the entities. And should sort get set to true when we call force sort. So that might be a little bit confusing, but the important part is that first it does some sorting, and then it iterates over the entities and calls processEntity. And we want to have our map rendering for now, which should not happen for each entity, of course. We just want to have that once. So that's why here we move that code here above. For the camera, let's also store the camera as a separate field. We could pass the camera here as an argument, but to keep it simple, we just take it out of the viewport. And that's it. So now every time the system gets updated, we do the map rendering as we had it before, and then we call super.update. And since we always want sorting, because our entities can move, for example, the player can move, and then dynamically we would need to change if the tree gets rendered before or after the player. So that's why we also call here force sort before we do the update call, so that the sorting is happening and then the processEntity calls are then happening. Okay, let's see. So we are currently missing the components. So let's create a new package. Let's call that component. And let's create here 3 classes. One would be, or let's start with 2 classes. So it would be the transform component and it would be the graphic component. So let's start with the more simple one. The simpler one is the graphic component. And there in Ashley, we have an interface, which is called component, that we are going to implement. And now we can attach the graphic component to an entity. And what kind of data do we need when we render something? We would need a texture region, and we also would need a color with which an entity gets rendered. We come back to that later on when we then creating the entities out of tiled. And yeah, then we need a constructor, of course, and the different getters. So the get region, get color, and also the region later on might change when we have animations and we use the different regions all the time. So that's why we also need here the setter. So that's the graphic component. And one special thing, which is also, I would say, rather common in entity component systems in Java at least, is a so-called component mapper, which gets created like that. So very, very simple. A component mapper simply is the fast way to access a component of an entity. It simply gives you can imagine that an entity component system in the background is just an array of different components. So we have an array of graphic components, we have an array of transform components, and the entity as mentioned initially, is just an ID in those arrays. And the lookup is then simply that in the graphic array, we pass in the entity ID, and then we know what graphic component the entity has. And yeah, to get then a specific component from an entity, there is a very similar approach. And instead of looking up the component via a class, which would be, I guess, some hash code calculation and then looking something up in a map or a set maybe, which is a little bit slow, it can be improved by using a component mapper, which is then simply creating a unique array index again for that specific component. So that's a mapper. And usually for every component that you want to access, you can just create a mapper in Ashley, and then you have the fastest way possible to get the component from an entity. Good, then for the transform component. So here, I just take over the code really quickly because I think typing all of that is rather boring, and then I just go through that step by step. Okay, so the transform component, again, it has a mapper so that we can quickly access it, and also that is the one that we used for when we go back to the render system. When we compare entities, we compare them by their transform component, where we also use the mapper to then get the transform component of an entity quickly and then compare it. And for transform, what do we need? We need the position of an entity, which is a vector 2D, so the x and y coordinate. We have a set information, which would mean if an entity is in the foreground or in the background. So that is an optional additional index for sorting. An entity has a specific size, which is also a vector 2. An entity can have a scaling to make it bigger or smaller, which is also a vector 2. And it can have a rotation in degrees, which is just a float. And yeah, so then we have the constructor of the transform component. We implement the comparable interface, and first we compare by the set value of the entity. Then, if the set value would be equal, then we compare by the y coordinate of the position. And if the y coordinate is equal, then finally we would compare by the x coordinate of the entity for the sorting. And other than that, it's just get us to get the information out of the component when we implement the rendering process. So coming back to the render system, I think if we would run the game, it should already work, but I want to implement also the processEntity method here, because then we are done with the render system and the logic that we add here doesn't change. So it's also a good example to see now how to get components and everything out of an entity and how to process then the logic, in that case for the rendering system. So again, for the render system, we get entities that have a transform component and a graphic component. So we want to work with these components. So what do we do? From the transform component, we use the mapper and get it from our entity. So we get the transform component, and in addition, we also need the graphic component. And now what we want to do, so if the graphic component, if the region is null, so there is no region specified to render for the entity, then we don't do anything, then we are simply done and we can return. But if we have a region, then we now want to render the entity. And how do we do that? So we get the position of the entity, we get the scaling, and we get the size of the entity. And now let's see what it suggests here. I just auto-completed, but let me check if that is correct. So first of all, we will set the color of the patch. So if the entity has a specific color, maybe it should be tinted in red or something, then we set the color of the patch to the color of the graphic component. And then we call the draw method of the patch to draw the entity, and there we pass in the texture region. That's correct. Then we position it at a specific coordinate, and we render it with a specific size. And I already see, so that is not correct what it did here. So the x coordinate is the position x minus 1f minus the scaling of x times the size x times 0.5. I explain in a moment what that means, because that might be confusing if you see it for the first time, what is happening here. But let me just finish here the coding. So that would be the x coordinate, that would be the y coordinate. Then we have something which is called origin, which is simply size x, half of it, size y, half of it. Then the real width and the real height. Finally, a scaling if we have it. And the last information would be a rotation if we have it. So this is everything that we pass to the draw method. And yeah, what does that mean? So again, when we draw something in OpenGL with the sprite patch, then we draw a texture. So just imagine it as an image. And the image needs to start at a specific position, which is usually the bottom left. And then it gets rendered to the top right. And what we do here, so with this position x minus something something, we simply adjust the position. So if there would be some scaling applied, so maybe to put it simple. So if there is no scaling at all, so if we just have a scaling of 1 and 1, so no scaling at all, then that one is here 0, and everything else below here after that is also 0. So if there is no scaling at all, it's simply position x and y. I think that is simple to understand and straightforward. But if we have some scaling, then we want to keep the image centered around its position. So when we stretch an image, maybe let me go back to tiled. So when we stretch, for example, the graphic, the way I want it, I don't want that the bottom left corner remains the same and the image just stretches to the right. What I want is that the position here is still the position of the entity, so that it gets stretched around its original position, like that. And yeah, the way it's working is with that part here at the end. Okay, then origin. Origin is the relative position when it comes to rotation and scaling, how it is applied. So if the origin would be 0, 0, then the rotation would also be around this bottom left corner, and the tree would go around like a clock. But like we have it, and that is, I think, the default value also for sprites in LibGDX, if it's half the width and the height, which would be exactly the center here of the graphic, then the rotation is around that center, and the tree would simply rotate here like a wheel. So it wouldn't go around this bottom left corner, it would go around the center and just rotate here. That is I would say, the good behavior. Then we have the size, so how large should the region be rendered? That is simply the size. Then if there would be some scaling, we pass the scaling values again. And the last argument is the rotation in degrees. So you see here the arguments again: region, x, y, origin, width, height, scaling, and the rotation in degrees. That is all that we pass in. And yeah, then it resets the color of the badge at the end, which is not needed here, because for the next entity, we anyway set the color again to whatever the entity has. Okay, so that was maybe quite a lot to process for the processEntity method. Maybe go through it slowly again and think it through, but that's it. So that method doesn't change for the rest of the tutorial. That is now done. And yeah, so I think we can try it out. Let's remove the asset service here for now, because it seems like it's not needed. It most likely comes then in a later part. So to summarize again, so we have our engine, we created or we added a system to it, which is the render system. When we load our map, we call the setMap method of our render system. And when we render, so when we have the update call, we update our engine. So we would end up in the render system and should see the map in the end. And when we dispose everything, we also dispose our render system, which disposes the map renderer. So that looks good. Let me start the program and see if everything is working. Perfect. So we see the map as we have seen it before. Oh, maybe I forgot to mention that I now adjusted the map to the repository map so that it looks the same as you find it on GitHub. That's the difference to the last part. I did that off screen to adjust here the map itself. Okay, but yeah, we see everything. Everything is working here again, which is great. So that is the basic concept of an entity component system approach. Again, we have the engine. We added now the render system. And we added components, transform and graphic component, which we did not use yet, but we will use that in a moment now when we are going to implement the loading of objects of Tiled. But since that part is already long enough, I would say, and there's also quite some logic that we have implemented, I would make a stop here and do the loading of the real entities then in the next part. So thanks for watching and see you in the next part. Bye bye.